Okay, so for this one we have another infinite series, and we have -1 to the n power over square root n squared plus 1. Okay, so for this one, we are asked to determine whether it converges absolutely, conditionally, or does not converge. Okay. All right. So on this one, we have that this is our given a sub n. Okay. So let's test for absolute convergence first. Okay. So just to start off, absolute value of a sub n is going to be the following. We're just going to stick this inside absolute value signs here. And remember I said when you have something in absolute value signs, the -1 inside is not going to matter when it comes out. So this is in effect going to be like that, right? Okay, so we've established that. And now we're going to look at this series, right, of the absolute value one. So this is what we got for the absolute value, an. So now to evaluate this, we have to use a variety of methods, kind of. So for this, I'm actually going to, well, this is our a sub n. I'm going to make bn, I'm going to use a comparison test here. So I'm going to make b sub n equal to 1 over n. Okay. So for this, I'm going to, okay, so we're using the, we're going to use the limit comparison test here. So we're going, this is our a sub n. Okay, so we're going to set up the limit. So we have L equals limit as n goes to infinity of a sub n over b sub n. So that's going to be a sub n. We're just going to rewrite that over b sub n, which is over 1 over n. And I'm just going to do this all in one swoop here and just flip it to come to the top. Okay. So then from here, we can rewrite this as limit. I'm just going to combine the numerator and denominator into n over square root n squared plus 1. Okay. So what we have here is, it doesn't look like much, but I'm actually going to, well, there's a variety of ways you could do this. You could either divide by, or multiply times 1 over n on top and bottom. But I'm actually going to take the different approach where we turn this into f of x form and then evaluate it from there. So I'll continue this on the next slide. So how we could rewrite this is the following. So what if we had limit as x goes to infinity? I'm just going to replace all the n's with x's. So I'm going to have an x over x squared plus 1. And then what I'm going to apply here is the integral test. And I just chose this method as opposed to the 1 over n thing, so I could demonstrate how to use other tests as well in combination with each other. So what we do here is take the integral from 1 to infinity of our f of x dx. So this is our f of x. So we just plug that in here, okay, and we add a dx to it. And then I'm going to use the handy dandy r for the improper integral, right? So we have 1 to capital R, and then we have an x over square root x squared plus 1 dx. And here again we have a u substitution, so we're going to sub that in, and for our du we get 2x dx, and again for dx equals du over 2x. Okay, so this comes out as limit as r goes to infinity of the following, and we're going to have an x over u to the 1/2, and then in for dx we're subbing in du over 2x. So then the x's cancel, right? So we have the x's canceling, and we get that this is limit as r goes to infinity. And I can rewrite the 1 over 2 out here. I'm going to bring the 2 outside in the front. And then this is the integral of u to the -1/2 du. Okay, so now we're just going to integrate like normal and see what happens, basically. Okay, so this is going to be a u to the positive 1/2, and then we'll have a 2 in front to compensate for that. And the 2 here cancels with the 1/2 in front, so that's good. And now at this point I'm going to replace it with the x's. So we have a square root, basically, of x squared plus 1. And now that I replaced it with x's, I can replace the bounds as well. So now we're just going to plug it in, plug in the r, I mean. So then we get square root of r squared plus 1 minus square root of 1 squared plus 1. Sorry, that's a 1. That looked weird. I'm just going to fix that here. So this is a 1 squared plus 1. Okay? And what we actually get is, when we plug in infinity, is infinity. So that means that this diverges. And going back, that ultimately means, I'll write that on the next page. This ultimately means that the infinite series of the absolute value of a sub n diverges. So, absolutely convergent, this a sub n is not. Okay, so it's not absolutely convergent. Okay, so now we're going to check for conditional convergence. So we have that a sub n is equal to, we have negative 1 to the n over square root of n squared plus 1. So we need to see if a sub n, like the terms itself. So now we're going to look at the magnitude. Remember, this just provides the alternating signs. So that would be like our plus, minus, this and that. So that provides the alternating signs part, but the substance of the sequence is going to be determined by everything else that's included in it. So I can kind of, like, we're just going to ignore the negative 1 for now. So let's write it as 1 over n squared plus 1. Okay? So we're going to check, is this itself always positive? And this is disregarding the negative 1. So is this always positive? Yes. And is it decreasing? Yes. Because as n grows, then the denominator grows, as the numerator stays the same, stagnant. So yes, it is decreasing. So that's good. And the third thing, this is the most important and, remember, is does this limit, and now this is considering the negative 1, so that's good. Does this equal 0? That's the big question mark here. Okay, so we're going to see, let's check the behavior of it. So if we actually plug it in, we would get negative 1 and over here. So this is, I'm just going to set it up the way it was given. So we have n squared plus 1. So this equals, let's say we plug in n equals 1. So we'll get negative 1 over square root of 2. Okay? And then for the next one, I'll just write them out. This is just plugging in, this is a1, that's a2, minus, and then a3 is going to be 1 over 10, plus, this is a3, and then I'll stop here. But then it just keeps going on and on and on, right? You could do however many terms. But the limit of this, as you might or might not notice, but you can see that each term in magnitude is decreasing. Magnitude means disregarding the signs, and the alternating part helps it converge to 0. So I'll write our conclusion on the next slide. So the limit as n goes to infinity of a sub n does equal 0. So yes, that is, the third condition is satisfied. So there's our big so. By the Leibniz, or I don't know, I feel like that's German or Austrian or some language that I've never taken a class in. So by this test of alternating series, then we can conclude after all of our work that this a sub n converges. But, and here's our but, the absolute value of a sub n does not. That diverges. So what we can conclude, this was from the first part. Remember when we tried to do the absolute value one and that didn't really work out? So when this converges, when the sequence itself converges but the absolute value of it does not converge and it diverges instead, then we have conditional convergence. Conditional convergence. So in essence, what this is saying, anytime I think of conditional convergence, is that the sequence itself, it's usually one with a factor of -1 in it, like to the n power or to the n minus 1. Those are usually the ones that converge conditionally. That means that it needs this -1, this factor of -1 of like going back and then forth and then back and then forth, like I've done on the number line various times. It needs that alternating part in order to converge to a certain sum. Okay?